Hello, Fast Physics here. So we're going to be looking at how rockets, for instance, escape a gravitational field. So the definition of escape velocity is that the velocity at which an object's kinetic energy is equal to minus its gravitational potential energy. So I spoke earlier about why it's a minus. See a previous video on what I did about gravitational potential. Now, this means the total energy for a rocket to escape is 0. I'm going to derive it. I'm going to show you why that is the way it is. But the first thing we're going to need is the equation. So for the escape velocity is square root of 2. Big G, which is 6.67 times 10 to the minus 11. Big M divided by your R. So this is really important that you don't get this all muddled up. Big G is a gravitational constant. M is the mass of the object you are trying to escape from, not the object that is doing the escaping. And R is the distance in which it's going to have to go. So that's the equation to start off with. I'm going to just show you now how to derive it. To start off with, as I've already said, we know our kinetic energy is equal to our gravitational potential energy. So I've just written out the two equations for us. The reason I've times it by m is we're now talking about the gravitational potential energy, not the gravitational potential. They're two separate things, so don't get them muddled up. So if I've got this, just to show you I'm not lying when I say it equals 0, another way of writing this is the following. So there you go, you can see where that minus is coming in now. So if I want to rearrange this, another way of writing that is like that. So looking back up to here, so imagine I'm taking this down here now. The first thing I can do is cancel out my m's. I'm going to try and colour coordinate this for you so it makes a little bit more sense. So I'm going to cancel out these two m's. Right? And that's going to leave me with a half v equals gm over r. Half v squared, sorry. Right, so we've got to this point. So if we want to rearrange for our v, that's what we're going to have to do next. So we'll rearrange for v squared to start with. So remember, if you're dividing by a half, you can take it up and times it by 2. It's doing the same thing. And last but not least, you just got to square root it. And there you have it. So, you just have to here have an example of how to derive the equation. You do need to know how to do it off by heart, back to front. So there you go. You can see the steps in which I've taken to do it. So for instance, if I wanted an example question, I'll just flip this over and write it out for you.
Several days later.
Okay, so now that I've written that out for you, let's have a go at doing this question. So you've got to just simply substitute in the value. So v equals the square root of 2gm over r. So it's going to be the square root of 2. G, as you know, is 6.67 times 10 to the minus 11. Your m is given in the question, so I can now cross that out. I've used this value up, which is going to be 5.98 times 10 to the 24. And then you got to divide it by your r, which is here. So I can say I've used that now. So that's 6.37 times 10 to the 6. If you smack that all into a calculator, it's sometimes worth doing the top, then divide it by the bottom, press equals, and then square root it. It's less likely to cause a calculation error. So do it all at once, then do it the other way just to double check yourself. And that comes out to be 11,190.7 blah, blah, blah. So that gives me 11,200 meters per second if it round it to 3 significant figures. Meters per second. Oops. So that's my escape velocity. That's how fast I would need an object to be going to escape the gravitational pull of the Earth's surface, which is pretty darn quick. So I hope that makes a little bit more sense to you, and see you next time. Bye.